Last time I introduced to you a class of reactions called electrophilic aromatic substitution. All of these have in common the need for a really reactive electrophile, because benzene is not that reactive, and all of them involve this key mechanistic pattern of pi electrons on benzene attack the electrophile, making a new sigma bond. You get to a high energy carbocationic intermediate where you have lost aromaticity. Then a base, and it doesn't have to be a very good one, even a very, very weak base like Br- or water can remove the proton on the carbon where you just made the new sigma bond, and then electrons kick down. This is sort of an E1 style elimination that's very fast, and it restores aromaticity. Overall, the net effect of this reaction is substitution. You swap out the proton that used to be there for your new, for an atom from your electrophile. Okay, this reaction rate is going to be determined by how nucleophilic the benzene ring is. If we can make the benzene ring more electron rich, that reaction is going to accelerate. If we make it more electron poor, the reaction is going to decrease. The other thing we're going to see is the structure of the carbocationic intermediate matters. If we can do things that stabilize that carbocationic intermediate by resonance, then we may make the reaction faster and more effective. So we'll talk about both of those issues, but first we need to introduce the 3 or 4 or 5 new reactions from this chapter and some of their downstream consequences. The second one that I introduced is aryl nitration. This is the substitution reaction where you swap out a nitro group for hydrogen, and the mechanism is as shown, follows that same pattern. I won't say much more about that. That is how you install a nitro group. When a little bit later in the class, we're going to talk about how these groups that we install on the benzene ring impact the reactivity of the benzene ring in the product relative to the starting material. We'll see that the nitro group is a great example of an electron withdrawing group, or one that makes the benzene ring less reactive. But there's another very important reason why you'd want to put a nitro group on a benzene ring, and that is there's other chemistry you can do with the nitro group. This isn't introduced till later on in your chapter, but it's a decent time to talk about it here. We will not worry about the mechanism of this reaction. This is a reduction reaction. You basically replace the nitrogen-oxygen bonds with nitrogen-hydrogen bonds. And again, we're not going to do the mechanism for this reaction, but this converts a nitrobenzene into an amine, and an amine that's attached to a benzene ring usually has the traditional non-systematic name of aniline. So this is a palladium catalyzed hydrogenation, reduces the nitro group to an aniline. The nitrogen is still there, but the nitrogen-oxygen bonds have been replaced with nitrogen-hydrogen bonds, and the nitrogen now has a lone pair. This is a reduction reaction. Its importance you may not appreciate at this point, but so far it's the only way we know of how to put an amino group on a benzene ring. The other importance is best illustrated by comparing the structures of the two groups, the nitro group and the aniline. Notice that both of them have nitrogens attached to the benzene ring, but that's where the similarities end. The aniline has a lone pair on the nitrogen, which we'll do this later in class today, but you could push electrons from the nitrogen to make a new pi bond there, and then you'd have to move these electrons over to put a negative charge on this adjacent carbon. That's what we call a resonance electron donating group. The aniline is a resonance electron donating group. It makes the benzene ring more electron rich. So increases the electron richness of benzene. And it also has another effect in terms of subsequent reactions that we'll talk about a little bit later. In contrast, the nitro group is a classic example of a resonance electron withdrawing group. It makes the benzene ring more electron poor. And you would expect that to slow down reactivity in subsequent reactions. How can you tell that this is a resonance electron withdrawing group? Here's the pattern. An atom bonded to benzene that is simultaneously pi bonded to an adjacent electronegative atom. That was a lot of words. I can't think of a more efficient way to say it. The pattern you're looking for is an atom bonded in a pi bond to an adjacent electronegative atom. When that happens, you should be able to see how I can move electrons from the benzene ring to form a pi bond here, and then these out there. We're withdrawing electron density from the benzene ring, thereby making the benzene ring more electron poor. So this pattern, this derivatization reaction, where we convert the nitrobenzene into an aniline, is important because it switches whether the benzene ring is electron rich versus electron poor, and that has some other interesting consequences later. So that's a reaction you'll just have to memorize in terms of the reagents and what happens. We're not going to do mechanism, but I've told you why it's important, and that's because we switch from something that's an electron withdrawing group to something that's a donating group. Yes?
For the electron withdrawing groups, are they always positive on that center atom?
No, our electron withdrawing group is always positively charged on the atom that's bonded to the benzene ring. It certainly helps, but no, there'll be examples where it's not. Okay, others? Yeah.
Your aniline, with it being an electron donating group, couldn't you do even more substitution faster?
Right. If you have the aniline, couldn't you do additional electrophilic aromatic substitution reactions faster? The answer is yes. In this case, these aren't conditions for those reactions, so there's no risk of anything bad happening in this derivatization reaction. But we'll see some problems with anilines in particular, and maybe now is a decent time to, well, no, I'll hold off on that for just a little bit. Okay, others? Let's do aryl sulfonation. I showed you this reaction in the last 30 seconds of last time. I've drawn the mechanism here. It's in your text. It's not hard. It's just another example of the same basic mechanism. You're using SO3 and then sulfuric acid. Your electrophile is probably protonated SO3. Where does the proton come from? H2SO4. That's not that hard. Probably benzene attacks the sulfur much in the same way that you would attack a carbonyl carbon. Then you break the sulfur-oxygen pi bond. And then that generates the same kind of carbocationic intermediate. Here was the proton we started with on that carbon, and it's still here. Here is the electrophile that we just added, and the hydrogen gets removed, and the SO3H remains. We can draw out that Lewis structure if you need a reminder of what that looks like. 2 pi bonds to oxygen, and then an OH group. And this is called an aryl sulfonic acid. If you've ever drawn H2SO4 before, this should look very much like it, only instead of having 2 OH groups, it's got a benzene ring on one side. You have seen sulfonic acids before. In the same family are TSOH, which you learned about in 351, which is an organic soluble acid that's just about as acidic as sulfuric acid. TSOH is an example of this. In TSOH, a methyl group would have been para to the sulfonic acid group. Okay, that's called aryl sulfonation. One thing to notice about the sulfonic acid group is that, like nitro, it follows the pattern of having an atom bonded to the benzene ring that is simultaneously pi bonded to an electronegative atom. So the SO3H group is likewise an electron withdrawing group owing to resonance, and it will likewise make the benzene ring more electron poor. Okay, There's not really any derivatization reactions we do with sulfonic acids after we make them. Meaning we don't have anything like what I showed you above where we convert the nitro group into an aniline for the sulfonic acid. So this is sort of we can do other electrophilic aromatic substitution reactions, but we're not going to turn the SO3H group to anything else. Okay, we got two more of these electrophilic aromatic substitution reactions. The following two are related to each other. They are both named after the scientists who discovered them. One is called Friedel-Crafts alkylation. Ooh, you guys aren't seriously excited by that, are you? You're mocking me, aren't you? I'm excited about it, but oh, you did it in lab. Okay, all right. You've done this in 353. Okay, that explains the ooh. I was like, I've seriously never seen a classroom of 20-somethings go ooh about the Friedel-Crafts reaction. I'm like, did someone break the universe? Okay. So you know about this. As before, the theme is going to be we want to attach an alkyl group to a benzene ring in place of a hydrogen atom. So same sort of substitution chemistry. The problem is that your typical alkyl halide as an electrophile is not good enough to make this process happen. So instead of just adding the alkyl halide, and it can be an alkyl chloride or an alkyl bromide, chloride is perhaps maybe more common, you must also add, like we did before for the halogenation chemistry, you must also add a Lewis acid catalyst. And the role of the Lewis acid catalyst is going to be to increase the electrophilicity of the alkyl halide. And it's going to do so in a very similar way to what we saw before for the halogenation reaction. That is, lone pair electrons on Cl are going to attack the empty p orbital on aluminum. Aluminum chloride has got aluminum bonded to three things. Aluminum is from the same column of the periodic table as boron, so it's got a nice empty orbital for the chlorine to attack. When it does so, the chlorine is now bonded to two things, and should have a positive formal charge on it, and then the aluminum should have a negative formal charge on it. I use green for my good leaving group, but I'm using green for other purposes. We'll go yellow. I don't know. I don't like it, but I've already chosen. This is now a super good leaving group. Okay? Now what happens next will honestly depend on whether your alkyl halide is primary, secondary, or tertiary. This is something that students typically hate, but it's reality, it's described in the text, so what are you going to do? For a primary alkyl halide of the kind shown here, what happens is the benzene ring actually does something akin to SN2 type chemistry where pi electrons from benzene attack the carbon that bears the leaving group, and the leaving group leaves. So that can be sort of SN2 style. At this point, the intermediate is going to be exactly the same as we saw before for other similar reactions. That is, we're going to have a positively charged carbon. There's our hydrogen, and there's the alkyl group that we just added. What I didn't draw, but I can, is the AlCl4 as the leaving group. And that can go back to Cl- and AlCl3, and we can regenerate the Lewis acid catalyst. At this stage, a base, probably Cl- or something else, doesn't really matter. It doesn't have to be a very strong base, removes the proton, and that gets us to our desired alkylated product. Okay, so that's if it's a primary alkyl halide. What people have observed in this reaction is that if you use a secondary alkyl halide or a tertiary alkyl halide, I'm just going to show you a secondary one for this particular example, that when you add the aluminum chloride catalyst, you generate the same kind of intermediate in which you've got a super good leaving group. But then, before the benzene ring attacks, the leaving group leaves. It's thought that this happens mostly because it can. In other words, the thought is that actually the benzene ring isn't a very good nucleophile, and the primary alkyl halide can't lose its leaving group because primary carbocations are too unstable. Once you get to a secondary alkyl halide, you can in fact lose the leaving group to give you a carbocation. And that carbocation is very reactive and will react quickly with the benzene ring. So there's some sense that this reaction is faster for secondary and tertiary alkyl halides. So this is sort of SN1 style, leaving group leaves. Then your electrophile is this carbocation. And electrons from the pi bond attack the carbocation. You're going to get, again, that very familiar intermediate that looks like this with a positive charge on the adjacent carbon. And then a base will remove the proton to make the pi bond, and we will get the restored product, restored aromaticity in the product. Yes? So yes, all of the things you've worried about can happen at this stage. So you may see some problems in which you should be aware of carbocation rearrangement. That is, be aware of when you form a secondary carbocation adjacent to a tertiary or a quaternary carbon, where a rearrangement could give you a more stable carbocation. I do want you to be aware of that. However, there's something in your text I want you to not care about. So I'm going to say something about it briefly. I don't want to take a lot of time in class to talk through something which I am subsequently going to tell you to ignore, right? Your text points out something that for primary alkyl halides that are longer than ethyl, you sometimes see rearranged products. And there's an explanation for it. It's kind of hard to rationalize, and we're not going to worry about it, okay? There is a workaround to avoid that fate that I will show you. You will see some questions on your problem sets and study guides where you want to make a benzene molecule like this, and your text will not do the direct Friedel-Crafts alkylation. They will take a more complicated route. The reason they are taking that more complicated route is to avoid the problem which I am telling you to ignore. Okay? So do not worry about rearrangement for primary alkyl halides like this. Do worry about the potential for rearrangement if it shows up if you have a secondary carbon that could be adjacent to a tertiary or quaternary carbon. The standard approach there is to draw both the rearranged and the not rearranged products, or in a mechanism question to be aware of the possibility for rearrangement if you need it to get to the product shown. Follow-up questions on all of that? I realize that was fast. Okay. Good. Yes?
Could you take the time to give us an example of that, or do we not?
I could, but I don't want to. It's in your text, though. So if you want to see the example of that kind of rearrangement of a primary alkyl halide plus leaving group in a Friedel-Crafts reaction, just look at the sections on Friedel-Crafts alkylation, and it'll be there. And you'll thank me for not talking about it. Okay, yes? Sorry, can't hear. Say it again. Is it possible for the positive charge to be here instead of there?
Or like just on the adjacent carbon.
Here? No, not possible. Why? Because that carbon is now sp2 hybridized. This is the carbon that gets the electrophile. It's sp3, it's bonded to 4 things. So yeah, the positive charge is always on the adjacent carbon.
Could you arrange that?
Rearrange this? Generally no, because this carbocation is resonance stabilized. So we haven't pointed this out, but notice that that positive charge is on these 3 carbons by resonance. So yeah, no rearrangement needed for that intermediate. Yes?
So what do we have to worry about? What do we not have to worry about
One more time for all the marbles.
for all of our?
I told you to be aware of the potential for carbocation rearrangement when you have a secondary carbocation adjacent to a tertiary or quaternary carbon. I told you do not worry about potential rearrangements for primary alkyl chlorides in Friedel-Crafts reactions that are bigger than ethyl. Though understand you're going to see in answers that your text will worry about it and you're going to have to suck it up. That feels good to say that. I say that to my teenager all the time. Yes?
For the real crash reaction, do we need to, can we use different halides? Like,
Could you use different halides? Bromides, yes. Iodides, I don't see any examples in the text. It's certainly a possibility. You'll see actually that in a problem in your text, anything that you might do to generate a carbocation, you can potentially do for a Friedel-Crafts reaction. So there's a fun example, I think, from your text where you have some kind of starting material and an alcohol and you use an acid, and it works because you just turn that into a good leaving group, it pops off, you get a carbocation, and then you can proceed. Okay, good. Sorry, erase. While we're on the subject of Friedel-Crafts alkylation, I want to point out that an alkyl group on a benzene ring is an example of an electron donating group that makes the benzene ring more electron rich. However, this is not a resonance donating electron donating group because there's no lone pairs on the alkyl group that you can donate into the ring via resonance. In fact, this is an electron donating group because of something called the inductive effect. You have heard those words before. Inductive effect usually has something to do with electronegativity differences. And if you look at the bond between the alkyl group and the benzene ring carbon, it's a bond between an sp3 carbon and an sp2 carbon. sp2 carbons are more electronegative, that's my abbreviation for electronegative, than sp3 carbons. Therefore, sp3 carbons can donate electron density through a dipole to an sp2 carbon. So the more alkyl groups you have on a benzene ring, the more electron rich the benzene ring gets. Okay? So we're going to see that alkyl groups are inductive electron donating groups. They will also make the benzene ring electron rich. Now, when the product of a reaction is more electron rich than the starting material, you do have to worry about the possibility of the product competing with the starting material for remaining reagents. That is a worry that your text talks about in a small amount of detail, but we will ignore. So there's some stuff in your text perhaps about the possibility for polyalkylation of benzene rings. That just means the monoalkylated product goes on to react again and add a second group. We're not going to worry about that. There's a pretty simple experimental workaround. We're just going to pretend like we always use it. All right? Okay. One other thing I will say about the Friedel-Crafts reactions, we're not ready to talk about this yet, but the presence of that aluminum catalyst with the empty p orbital on the aluminum is really important. anything that might interfere with or bond with that aluminum or donate its electron density into the MTP orbital can interfere with the Friedel-Crafts reaction. So in a few minutes or on Friday, I'm going to tell you that some starting material doesn't work well in a Friedel-Crafts reaction. And the reason it doesn't is because the starting material itself interferes with the aluminum catalyst. That's just a preview. We'll come back to that a little bit later. Okay, other questions there? Okay, while we're on the subject, I'm going to show you, did I miss a hand? You were pointing. Yes, Miriam, thank you.
So if we added more electron donating groups as substitutes to the benzene, would that favor Friedel-Crafts?
So if we added more electron donating groups to the benzene ring, would that make the Friedel-Crafts reaction faster? Yes, provided they didn't interfere in the way I just described. Yeah. Okay, I want to talk about derivatizing Friedel-Crafts products. There are a few, and this is to help you out with synthesis questions. There are a few reactions you can do on the product of a Friedel-Crafts reaction, which is an alkyl benzene. As before, with these derivatizing reactions, derivatizing alkyl benzenes, we're not going to worry too much about the mechanism. Some of them are familiar, some of them might be new. There's going to be maybe 2 or 3 of them. And I just want you to be aware of them because they increase your, and be able to use them in a synthesis because they increase your options. So, for example, if we made ethyl benzene, which is one of the ones I just described to you previously, you can do radical halogenation from chapter whatever it was of 351 using bromine and light or whatever other method you want to use for generating radicals. And the product installs a single bromine on the carbon that's adjacent to the benzene ring, okay? And we call that carbon that's adjacent to the benzene ring the benzylic carbon. That's just a term that organic chemists use. I may use it, understand, I'm using it because it's shorter than saying that carbon there, you know, the one that's adjacent to the benzene ring. I can accomplish all of that with benzylic. So that's what we're going to do. That's the benzylic carbon. The reason, and I won't show you the mechanism of this reaction, though you could get it if you go back to the radical chapter. The reason the reaction is selective for putting the bromine on the benzylic carbon is because it involves an intermediate that looks like this, in which you have a radical on the benzylic carbon. And that benzylic radical intermediate is more stable than any of the other options that you can think of. Remember that in radical reactions, you usually have some radical, whatever it is, in this case it's probably Br radical, abstract a hydrogen atom from the benzylic carbon like this. And the question is, why is that benzylic radical intermediate more stable than the other options? What do you got? Resonance, yeah. Actually, the radical can be stabilized by resonance with the benzene ring. So this is a resonance stabilized radical intermediate, and that's why you get the bromine on the benzylic carbon. Once you've got it there, you can do all kinds of things, right? You can do SN2 with alkyl halides. You can do E2 eliminations with alkyl halides. Those are both 351 reactions. If you ever see a product that you need to synthesize where you've got the double bond adjacent to the benzene ring, this is how you do it. Some of you are going to come to me and say, why, and say you invented chemistry, why can't I just use this in a direct Friedel-Crafts alkylation and put that group on there? The answer is that we typically don't do, remember that the mechanistic steps from Friedel-Crafts were basically either SN2 or SN1. We don't typically do SN2 or SN1 at sp2 hybridized carbons. So if you see the double bond attached to the benzene ring, this is how you do it. You alkylate first, radical brominate on the benzylic carbon, and then eliminate to get the double bond in the right place. So you maybe have a chance to work on that through some synthesis. So that's one of the derivatizing reactions. And that's the one that makes the most sense. The other one is sort of mind-blowing. We don't necessarily use it a lot, but your text talks about it. And it is a way to switch an electron donating alkyl group into something that's electron withdrawing. So here is, again, ethylbenzene. It's an alkyl benzene. And your text shows a couple of conditions for doing this. I'm just going to do one. We're using potassium permanganate, or KMNO4. This is an oxidation reaction. Potassium permanganate, that manganese metal is in the +8 oxidation state. So it's highly oxidizing, and it can do things that other reactions can't do. For example, and you're not really going to believe this, but it happens, it will cleave all of the carbon-carbon and carbon-hydrogen bonds with the benzylic carbon. It leaves the benzylic carbon in place, and it replaces those 3 bonds with bonds to oxygen. That's sort of wild magic chemistry. I don't have a mechanism for it. I could look it up, but I don't understand it. And I don't care that much. But notice that this converts something which was an inductive electron donating group into something that fits the pattern for being a resonance electron withdrawing group. That is, you have a carbon, at the benzylic position, you have a pi bond to an electronegative atom. Okay? And of course, you can do all sorts of things with carboxylic acids, right? So this is chapter, whatever it was that 16 or 17? I don't remember, but you can do nucleophilic acyl substitution type reaction to convert carboxylic acids to esters, amides, etc. Okay, questions about that? I know it's a lot. Okay, the final new set of reactions is called Friedel-Crafts acylation. This is basically like Friedel-Crafts alkylation, only the thing that you're going to add instead of being an alkyl halide is an acid chloride. So here I'm just going to be general and put some kind of R group. What I've drawn here is an acid chloride. And then we're going to use the catalyst aluminum, AlCl3, aluminum chloride. This is going to swap out the hydrogen on the benzene ring for the acyl group of the chloride. So this thing. Uh-oh. And this may be the reaction that you did in the 353 lab. Like alkylation, the mechanism begins with lone pairs on the chlorine attacking the aluminum chloride catalyst, thereby turning the chlorine into an even better leaving group with a negative formal charge on the aluminum and a positive formal charge on the chlorine. Now, it turns out that is such a good leaving group, it's now in fact a neutral leaving group, that a neutral oxygen can kick it off. We've talked about neutral oxygens kicking off neutral leaving groups before. So what your text says happens is actually the neutral, and this is the one time we've ever seen this. This is unique in carbonyl chemistry. This is the first time you've seen this. Lone pair electrons on the neutral carbonyl oxygen kick down to form a second pi bond, and the leaving group leaves. The product that's made when you do that, now the carbonyl carbon has to be sp hybridized. It's bonded to only 2 different things, 3 pi bonds, or three bonds, 1 sigma and 2 pi. The oxygen has a positive formal charge, And you could also draw the resonance structure as that. And this intermediate is called an acylium ion, which is kind of a silly name, sorry. Couldn't resist. Sometimes the dad jokes just come out of me without me trying. All right, that acylium ion then is the electrophile in the subsequent reaction. Everything from here on out is going to be exactly the same as you've seen before in similar electrophilic aromatic substitution reactions. You may pick and choose to your heart's content whether you want to push arrows to this resonance structure of the acylium ion or to this one. Either of those options is okay. They communicate the same thing. Benzene pi electrons attack the carbonyl carbon to make a new carbon-carbon sigma bond. Okay, and the intermediate that you get looks like this. Again, we're going to have an adjacent positively charged carbon and then a carbon where we just attached the electrophile. Then a base, we don't care what it is, possibly Cl minus, removes the proton, electrons kick down, and we restore aromaticity. And this is the group that just got installed. Generally, the R group here is something that is alkyl or aryl, that is, it's carbon-based. All right. Questions about that mechanism? We want to pause to notice that the group we have just installed fits the pattern for a resonance electron withdrawing group, meaning we would expect it to make the benzene ring more electron poor. Okay? Let's see. Others? Yeah.
If it's more electron poor, it's going to be less reactive, correct?
That's right. It will be less, if it's more electron poor, it will be less reactive as a nucleophile. Saw another hand.
Yeah, can we assume to be carbocation rearrangement with that?
Is there carbocation rearrangement in the acylium ion? No. The presence of that oxygen stabilizes. It's the acylium ion, as you've seen, is resonance stabilized. So there's no risk for rearrangement. Okay. Okay, as before, we're going to introduce one new derivatization reaction for the what we will call acyl benzene. This is the benzene with the acyl group. I'm doing this because it's kind of a cool reaction, and it likewise switches an electron withdrawing group to an electron donating group. Your text uses this as this new reaction as a workaround for a problem that I told you not to worry about. Nevertheless, I'm going to show you the reaction because it's kind of cool. The reagent here is one that I don't think you've seen before. It's something called hydrazine, which is used in other contexts as jet fuel. But the hydrazine will replace both bonds between carbon and oxygen with bonds to hydrogen. The mechanism for this reaction is known, and if you are curious about it, please come talk to me. I would be happy to talk you through it. It's kind of cute. It involves imine formation and proton transfer, imine formation and tautomerization. Ultimately, you lose nitrogen in the process. We don't need to worry about that mechanism, but as you've seen, it converts something that used to be a resonance electron withdrawing group into something that is now an inductive electron donating group. So there's that switch between the two. There's another set of reagents in your text that does this as well. I'm not sure to what extent your text makes this apart. I'm not going to ask you about these other reagents, but if you see them, A zinc-mercury mixture will also do this. We're not going to talk about that in any level, nor am I going to ask you questions about it on the exam. You might see it in the study guide if you're doing specific problems. Now you know what to do with it. All right, so that's all the new reactions. We've taken time to go through and talk about each group that we've attached to the benzene ring and note which ones make the benzene ring more reactive versus less reactive. I want to go back to one that we didn't do that for, and that was the very first one, the halides. Okay? The halides are weird. So that's maybe a conclusion that you can draw for groups that are from benzene rings, because they have dual character. The halide fits the pattern that the aniline has for a resonance electron with electron donating group, because you've got lone pair atoms adjacent to the ring. However, it also fits the pattern for an inductive electron withdrawing group, in the sense that the halide is more electronegative than carbon, and so it can pull via a dipole electron density out of the benzene ring. So the halides have this dual character. It turns out that in terms of reaction rate, aryl chlorides or aryl halides generally are more electron poor than benzene. So that means they will react more slowly in subsequent reactions. However, I want you to keep in the back of your mind the idea that halides are resonance electron donors, because that's going to explain a result we will see in reactions of benzenes that already have a group on them in subsequent reactions. Okay, so halides are inductive withdrawers but resonance donors, and we'll talk about the trade-off between that. All right, we're going to spend the rest of our time today and Friday on what happens when you want to do an electrophilic aromatic substitution reaction on what I'm going to call an already substituted benzene. That is a benzene ring that already has something on it. So let's start with, say, a benzene ring that has a methyl group on it already. You've learned how to put methyl groups on benzene rings. That's a Friedel-Crafts alkylation. Suppose we want to do a subsequent halogenation. Let's just do aryl halogenation, which is Cl2 with FeCl3. When we first did aryl halogenation with just benzene, it did not matter which carbon attacked the electrophile, because the carbons of benzene were all identical. Now that illusion is over. There is no such identity. In fact, you have 3 different carbons relative to the group that is already attached, already substituted. Okay? You have what we're going to call the orthocarbon. Ortho is, I think, a Greek word for right, the right-hand side, or you'll think orthogonal means at a right angle. The orthocarbon is here to the left of the carbon we're talking about, so I don't know why they're using it. But the carbon that's adjacent to the group that you're interested in is called the orthocarbon. Ortho is a relative term. It just means the 2 groups are adjacent to each other on the benzene ring. We'll abbreviate that with the letter O. The next carbon is meta. I'm not sure why we use that. Oh, it's so meta, dude. Do hipsters even know what that means? I don't know. I'm not sure I know what it means. And then the last one we're going to call para. Okay? So para is the carbon that's opposite the group that we're talking about. Ortho is the one that's adjacent. Meta is the one that's 2 carbons away. So you have to worry about regioisomers. The question that you're going to ask is, does the new chloro group get substituted at the ortho position like this? This is the ortho product. Does it get substituted at the meta position? That's the meta product. Or does it get substituted at the para position? That's the para product. And the answer is that we exclusively see for this reaction ortho and para regioisomers. We do not see the meta isomer. And by not observed, I mean less than a certain amount. Generally, we see pretty high selectivity for ortho and para products. Okay? There's a connection between the identity of the group on the benzene ring, this inductive electron donating group, and the regioisomers that we observe. In fact, we call inductive electron donating groups ortho-para directors. Because generally, if you have an electron donating group attached to a benzene ring, and you do a subsequent electrophilic aromatic substitution reaction, you see ortho and para products. That's true also for resonance electron donating groups. So, as an example, here is a methoxy group on a benzene ring. We haven't learned yet how to put that there, and we won't actually until after the second exam. But suppose you did an aryl nitration reaction where you install a nitro group. Again, we would expect to see as products the ortho nitro group and the para nitro group, and we would not expect to see any of the meta isomer. And again, there is a connection between the fact that this is a resonance electron donating group, which we will come to see is an ortho and para directing group, and the fact that we observe only ortho and para products. Now, I haven't told you the reason for that. It's not difficult to see, but you have to take a few minutes and draw the carbocation intermediates that would form for the ortho product versus the para product. I'm sorry, for the ortho product versus the meta product. Before you come to class next time, I want you to try to do that and try to see if you can tell me why the carbocation for ortho substitution is better than the carbocation for meta substitution. All right, that's enough for today. I'll see you Friday.